So this is why the handout okay, so in my Google Classroom announcement, the second article is definitely worth reading. And because the first topic is linearity of expectation, and the second topic is recursion, which is what we're about to use here. And so we're going to define A sub n to be the number of ways to fill a 3 by n rectangle. So note that our answer will be A sub 15. And it's always better to like keep in sight what the final goal is. The final goal here is to find A sub 15. Because A sub 15 is the number of ways to fill a 3 by 15 rectangle with 1 by 3, yada, yada. Okay. And so now, as I said earlier, foreshadowing, we're going to use recursion. So how do we, I mean, at first glance, it may seem like, why are we solving it for general n instead of just for 15? And just R. It makes it a lot more simple. It makes it a lot more scalable, like getting from like, oh, you'll see. Okay. And so now we can try to find a relation on A sub n. I'm trying to find a way to like define it. So let's draw 3 by n. We've been doing a lot of talking, but have not actually seen a 3 by n rectangle. So there's 3 points over here. And so now we can do some casework. So let's consider this special square. This one will have to be filled eventually. So how do we fill it? Well, there's 2 possible ways that we can fill this. I'm going to duplicate. Just going to duplicate this. Okay. There are 2 possible ways. Case number 1, we put in a vertical block, in which case we do this. Case number 2, we fill it in horizontally. Just like that. And then, okay, so in case 1, we're left with n minus 1. So the number of ways to complete the other n minus 1 is just going to be n minus 1. Whereas on this side, the number after putting in that one, how do we fill in this? The only way to fill in this red square will be to do this. And after that, how do we fill in this square? Well, we have to complete it once again. And so this, we're left with n minus 3 squared. Look at that. That's A sub n minus 3. So we've shown that for all n greater than or equal to 3, A sub n equals A sub n minus 1 plus A sub n. Very important. This is, I'll even label it. That's our most important identity. And after that, we can just find A sub 1, A sub 2, A sub 3, and then boom, let's just start computing. So let's do that. This is exactly what I did in the PDF. So A sub 1 equals, how many ways can we fill in a 3 by 1 rectangle with 3 by 1 rectangles? 1 way. A sub 2, how many ways can we fill in a 2 by 3? Well, we have to do them vertically. So A sub 2 will be 1. Now A sub 3 will be A sub 2 plus A sub 0, that will be 2. And after this, there's nothing very special. We're just going to run through using this relation all the way down to 15. So I'm just not going to talk. I'm just going to write it out. So a sub 4 equals 3, a sub 5 equals 4, a sub 6 equals 6, a sub 7 equals 9. Yep. A sub 8 equals 13, a sub 9 equals 19, a sub 10 equals 28, a sub 11 equals 51, a sub 12 equals 70. Doesn't seem right. Nope, it's not ace. Okay, so a sub 11, in fact, equals 41. A sub 12 equals 60. A sub 13 equals 88. A sub 14 equals 129. And a sub 15 equals 189. And that's going to be your final answer. So the main idea here was to generalize this to a 3 by n rectangle, because there's nothing in like remarkable about 15. Like nothing that's true about 15 is not going to be true. There's nothing in a 3 by 15 rectangle that's like substantially different from a 3 by 16 rectangle. So we can just solve it generally for any n and just makes it easier. Otherwise, I mean, technically you could do this with casework, but that sounds rough.